Welcome to AI Paper Podcasts. We cut through the noise of the latest research and get you straight to the key insights. Today, we're diving into one of the really big questions right now in the world of large language models. How well do these new diffusion LLMs actually handle really long stretches of text? Everyone's talking about them, but their long context abilities, still a bit of a mystery.
Exactly, and that's the mystery we're digging into today. We're looking at a really foundational paper called LongLLaDA, Unlocking Long Context Capabilities in Diffusion LLMs by Xiaoran Liu and the team. And this isn't just, another paper. It's really the first to systematically tackle this, putting diffusion LLMs like LLaDA head-to-head with the more, let's say, traditional auto-regressive ones like LLaMA3.
And what they found is, well, honestly, pretty eye-opening. First off, maybe the biggest surprise, this remarkably stable perplexity in the diffusion models, unlike the auto-regressive ones that, often just fall apart with too much text. These diffusion models just keep their performance steady, really stable, even when pushed way beyond their training length.
Yeah, it suggests something fundamentally more robust about their architecture for handling huge inputs.
Huge.
And then there's the retrieval side. They show this really fascinating effect the paper calls local perception, kind of like a sliding window. So even with a massive document, they can still reliably grab info from the most recent chunk. It's totally different from auto-regressive models, which often just, fail. They give up.
Okay, and the why behind this, it's really interesting, right? It's tied to their position embeddings.
Precisely. It's all about their rotary position embeddings, or RoPE, and how they process positional information. The key is the bi-directional attention they use during training. It gives them a much richer understanding of position.
Like you see forward and backward.
Exactly. And building on that understanding, they developed LongLLaDA. This is a really neat training-free method. It uses NTK-based RoPE extrapolation, and the result, they managed to extend the context windows for these diffusion LLMs by up to 6 times. So think 4,000 tokens becoming 24,000 tokens, all without retraining.
Wow, okay. 6 times.
Yeah.
So on actual long context tasks, how do they stack up? What's the practical takeaway here?
Well, they're actually really good at retrieval and question answering. That seems to be a strong point. But they do lag behind a bit on aggregation tasks compared to the auto-regressive models. So for anyone building or working with these advanced AI models, this deep dive gives you a kind of roadmap for pushing the limits of what diffusion LLMs can do with really long, complex stuff.
Okay, let's maybe zoom out just a tiny bit. Why are diffusion LLMs such a hot topic anyway? What are they trying to fix that the older models struggled with?
That's a great starting point. They really are seen as a new frontier in NLP. A lot of hope is pinned on them for tackling these persistent issues. Things like the reversal curse, where a model learns A is B, but then can't figure out B is A.
Right, that basic inference step.
Yeah, and also complex reasoning, maintaining coherence over really long texts. These are things auto-regressive models have often, stumbled on.
So it's fundamentally a different architectural bet for solving some core LLM limitations.
Precisely. And there's been a ton of work recently validating their scaling, adapting them for multimodal stuff, text and images together, like MMATA, LLaV, LLaVITA, plus applying them to tricky reasoning tasks, models like D1 and D-T, and of course making them run faster, more efficiently with things like Decay cache and Dimple. But the big missing piece until this paper really was a deep, systematic look at how they handle long context.
Right, so to get at that, the researchers set up these really clever initial experiments, pitting LLaDA, the diffusion model, against LLaMA3, the auto-regressive one, looking at perplexity and that Needle-In-A-Haystack task.
And the perplexity results are, they're pretty stark. If you look at the graph in the paper, figure 1A, you see LLaDA at EB base trained on 4K tokens. Its perplexity line stays incredibly flat as the context length goes up, way beyond 4K.
Just stable.
Super stable. It just doesn't get confused by the extra length. But then you look at LLaMA3 8B, trained on 8K. As soon as you go past 8K tokens, its perplexity shoots straight up, skyrockets. It's a total performance collapse. It really highlights a fundamental difference in how they're built to handle context length.
That's a massive difference, yeah. One just handles it, the other breaks completely. And then the Needle-In-A-Haystack task. Can you remind us what that involves?
Sure. It's basically testing if a model can find a tiny, specific piece of information, the needle hidden inside a really long document, the haystack.
Like finding one specific sentence in a giant book.
Exactly, a tough test. And the results there were also super interesting. LLaMA3, perfect accuracy within its 8K training length, but go beyond that, 0. It finds absolutely nothing.
Total failure.
Total failure. Now, LMADA gets 100% within its 4K context, but here's the kicker. Even when you push the context way out to, say, 24,000 tokens, LNA still finds the needle sometimes, but it tends to find it if it's within the nearest 4,000 token window.
So that's the local perception or sliding window effect you mentioned.
That's it precisely. It's not a complete failure like LMA3. It's more like its attention is focused locally on the most recent part of the input it can effectively see.
That's fascinating. It fails differently. And I saw something about sampling steps making a difference too.
Yeah, that's another layer specific to these diffusion models. The number of sampling steps, basically how many refinement passes it makes, does influence how deep it can retrieve in that NIH task. So with LLaDA base using just 1 or 4 steps, it mostly failed beyond 8K tokens, like you might expect. But if they cranked up the steps to 8 or 16, it actually started getting some hits even at 16K tokens, maybe 25% accuracy, and even a little bit, almost 10%, at 24K tokens. So the sampling strategy matters. It can push the boundary a bit, but it's still working within the fundamental limits set by the architecture and that local perception.
Okay, let's unpack this then. We've got this stable perplexity, this weirdly cool local perception.
Yeah.
But how? What's actually going on under the hood that lets diffusion LLMs do this?
Right, this is where we get into the mechanics. And it really boils down to the rotary position embeddings, RoPE, and crucially, the fact that diffusion LLMs are trained using bi-directional attention. They see context in both directions.
Bi-directional attention. So that's the core difference compared to auto-regressive.
That's the fundamental thing, yeah. Think about how they learn positions. Auto-regressive models like LMA3 learn relative positions going forward, from 0 up to, say, 8191 for an 8K model. When you try to go beyond that 8K limit, they haven't really learned about those further positions or negative positions effectively. Half their embedding space related to position is kind of unexplored territory, like they only learn to look right.
Okay.
Diffusion LLMs, though, with bidirectional attention, they learn a symmetric range, both forwards and backwards. So for a 4K LNA, it learns relative positions from -4095 all the way up to +4095.
A full circle almost.
Exactly. This symmetric coverage, even though LLaDA's training length, 4K, is shorter than LMA3's 8K in this comparison, lets it capture the full cycle of the sine and cosine functions used in RoPE. That complete picture of relative positions is key to why they handle extrapolation so much better.
Okay, that makes sense for the stable perplexity. They have a more complete map.
Yeah.
But why the local perception then? If their map is so complete, why don't they just see everything perfectly, even at 24K? Why the decay in the NIH task?
That's a really good question. It comes down to the properties of the cosine function in RoPE, which is mostly responsible for encoding the distance. Cosine is an even function. It's symmetric around 0, right? Cosine of x is the same as cosine of -x.
Right.
So while having those negative relative positions makes the representation robust, it doesn't actually increase the maximum distance the model effectively learned to perceive during pre-training. So the model tolerates positions outside its training range really well, hence stable perplexity. But its inherent sense of reach or maximum perceivable distance isn't fundamentally extended just by seeing negative positions. That's why it still defaults to that local window in the NIH task.
Got it. Robust to new positions, but still focused locally.
Yeah.
And the paper had those cool visualizations, the TSNI plots. They back this up.
They really do. Figure 5 is quite telling. You look at the internal states, the QK starts for LMA3. When the positions go out of distribution, beyond 8K, you see these clear shifts, new clusters forming. The model's internal geometry changes. It gets confused.
Yeah.
But for LLaDA, you compare the states from within its 4K training range to those beyond 4K, and there's almost no shift. The pattern, the manifold, stays remarkably uniform. It's visual proof that LLaDA's internal representation doesn't freak out when it sees these out-of-distribution positions. It handles them gracefully, which connects back to the stable output and that local perception.
That's really compelling visual evidence. Okay, so now we understand the why much better. Can we actually use this understanding to push that local window out further, to extend the context?
Yes, exactly. And that's the whole point of LongLLaDA. It's this elegant, training-free approach the researchers came up with. They realized that even though diffusion models have these unique properties, the underlying math for RoPE extrapolation, specifically NTK-based scaling, should still work. It's been successful for autoregressive models. Why not here?
NTK scaling. Can you give us the simple version of how that works?
Sure. Think of it like adjusting the focus or zoom level for the model's positional sense. It slightly scales the rotary base frequency used in RoPE. This scaling tricks the model into interpolating positions it hasn't explicitly seen during training, making it think these new, longer distances are just scaled versions of distances it already knows. For LLaDA, they used its specific rotary base, 500K, and pre-training length, 4K, to calculate the scaling factor. Lambda needed to target longer contexts like 8K, 16K, or 24K.
Clever. Like giving you new glasses.
Pretty much. And the results. Figures 6 and 7 show it working beautifully. With a lambda of 4 targeting 8K context, or lambda 14 for 16K, LongLLaDA gets almost perfect recall across all the different depths within those new extended ranges. The effective window of perception ggets pushed way out.
So it extends the context and the effective reach of that local perception. Is there a limit, though? How far can you push it?
There seems to be. When they tried lambda 31 aiming for 24K tokens, they started to see that lost in the middle issue pop up where performance dips for information right in the center of a very long context.
Ah, okay, a known issue even in other models.
Exactly. It suggests they're hitting the practical limits of the specific extrapolation method around there. And going further, like lambda 55 for 32K just didn't really work well, but still achieving that 6x extension 4K to 24K without any retraining, that's a huge validation that these RoPE scaling techniques work great for diffusion LLMs too. A big win for efficiency.
Definitely a big win. Okay, so we can extend the context, awesome. But the crucial question remains, how do they perform on real long context tasks compared to the established auto-regressive models? Where do they excel and where do they maybe fall short?
Right, performance is key. They tested this using LongBench and ruler benchmarks. On LongBench, LLaDA was generally stable and performed decently well, even beyond its original context limit. Overall, pretty comparable to LaME 3. One interesting point was LLaDA did consistently better on the synthetic tasks in LongBench. These are often designed to probe specific capabilities.
Okay, comparable overall, maybe better on specific synthetic tests. What about ruler? That one breaks down task types more, right?
Exactly. And ruler reveals some really clear distinctions. On the Needle-In-A-Haystack type retrieval tasks, diffusion LLMs like LLaDA actually match the performance of the auto-regressive models. Single key, multi-key retrieval, they hold their own.
Aggressive.
Very. But then you look at aggregation tasks, things like tracing variables through code or finding the most frequent word in a long text. Here, the diffusion LLMs really underperformed, significantly worse than the auto-regressive models.
Ah, so finding facts is fine, but summarizing or combining information across the whole context is a weakness.
That seems to be the case, yes. It's like they struggle to synthesize information gathered from multiple points across the long context. That's a clear area where auto-regressive models currently have the edge.
Okay, clear weakness there. But what about question answering? You mentioned that earlier.
Yes, and this was maybe the biggest surprise on the task performance side. On QA tasks, using datasets like Squad and Hotpot, diffusion LLMs like LLaDA actually showed superior performance. These are tasks where auto-regressive models sometimes struggle with long contexts or complex reasoning chains. LLaDA seemed to handle them better.
Wow, okay. So, to summarize the performance, comparable on retrieval, weaker on aggregation, but surprisingly stronger on question answering.
That's the picture right now, based on this research. It really paints a picture of diffusion LLMs having their own distinct profile of strengths and weaknesses compared to auto-regressive models.
So let's bring it all together. What does this mean for the bigger picture, for the future of LLMs, and maybe for you, the listener, if you're an AI researcher or an ML engineer building things?
Well, I think this paper is really important. It's the first deep, systematic look at long context in diffusion LLMs. It identifies their unique behaviors, that stability, the local perception. It gives us LongLLaDA a practical, training-free way to extend their context. That's huge. And it provides these crucial benchmarks showing where they shine and where they need work. It lays the groundwork for a lot of future research into optimizing these architectures.
Yeah, it feels really foundational. And for you listening, this shows a potentially powerful new direction for handling huge amounts of text or data, especially if your application leans heavily on, say, question answering or precise fact retrieval over long documents. That QA advantage is particularly intriguing. So, quick recap. Diffusion LLMs. Surprisingly stable with long text, they have this unique local perception. LongLLaDA lets us stretch their context window way out, training free. And performance-wise, great at QA and retrieval, but need work on aggregation.
Exactly. And maybe a final thought for you to chew on. This paper really focuses on inference time extrapolation. The authors themselves point out that exploring fine-tuning methods specifically for long context or digging deeper into how different sampling strategies interact with these extended contexts, that's a big next step. How could those techniques further boost performance, maybe even address that aggregation weakness? What could that unlock for the specific AI problems you're trying to solve?
Great question to ponder. We definitely encourage you to check out the paper itself, LongLLaDA, explore the models if you can, and really think about how these unique diffusion model characteristics might shape the future of AI systems. Thanks for diving deep with us on AI Paper Podcasts.